Let us explore the intriguing and controversial idea that atoms are not tiny static particles, but vortexes, whirling patterns of motion within an all-pervading medium, historically called the ether. This concept, while largely abandoned by mainstream physics, is making a quiet return in theoretical circles seeking to unite quantum mechanics and space-time geometry. But is there any scientific basis to consider matter as condensed rotation rather than solid stuff? Let us begin with a question. What is an atom, really? In modern quantum theory, an atom is mostly empty space. The nucleus, protons and neutrons, sits at the center with a cloud of electrons described by wave functions spread out around it. These electrons do not orbit like planets, but they do have angular momentum, meaning they are inherently rotational in character. So already, the basic components of atoms involve spin and motion, not static balls. Now imagine extending this further. What if the particles themselves were not objects but stable patterns in a field, vortexes, in something deeper? In the 19th century, before quantum mechanics took center stage, some physicists believed in the existence of an invisible medium called the ether, a kind of cosmic fabric through which light waves propagated like sound through air. Scottish physicist William Thomson, Lord Kelvin, proposed a daring idea. What if atoms were knots or vortex rings in the ether? These swirling patterns would be stable due to their topological properties, meaning they could not easily unravel, and this stability would correspond to the permanence of atoms. You might ask, was this idea ever tested? In a way, yes. The idea fell out of favor after the famous Michelson-Morley experiment in 1887, which failed to detect Earth's motion through the ether. Later, Einstein's theory of special relativity removed the need for a fixed background medium altogether, and the ether concept was largely discarded. However, modern quantum field theory, QFT, brought back something similar in spirit. Instead of ether, we now talk about quantum fields, permeating all space. So what is the modern reinterpretation? In advanced physics today, some researchers explore the notion that space itself may be an emergent phenomenon, and that particles, such as electrons or quarks, could be viewed as topological excitations or vortex-like knots in an underlying field. In loop quantum gravity, for example, space-time is seen as a network of loops or spin foams, and matter arises as knotted distortions in this fabric. Similarly, in pilot wave theories, particles are guided by a hidden subquantum field which behaves like a fluid. Let us ask, could this explain why matter is stable? Possibly. If particles are not fundamental things, but emergent behaviors, stable vortex-like solutions in a deeper substrate, then their persistence and discrete properties like mass, charge, and spin might arise from the geometry and dynamics of this hidden layer. Some physicists like David Bohm even proposed that the universe behaves like a hologram, with particles emerging from deeper, more ordered structures. In such a view, what we call matter is more like a ripple or rotation in the quantum ether, not a billiard ball, but a swirl. Here's a helpful analogy. Think of a whirlpool in water. The water itself is everywhere, but the whirlpool is a localized, rotating pattern. It seems like an object, but it's really just a dynamic behavior of the medium. This is how atoms might be viewed in etheric or topological models as vortexes in the quantum field, where rotation creates the illusion of a particle. Another question, does this have any observable consequences? This is where it gets tricky. So far, standard quantum mechanics and particle physics work extremely well without assuming an ether. But new theories like superfluid vacuum theory, zero-point field models, and even emergent gravity are trying to test whether vacuum fluctuations or field vortices can be detected indirectly, for instance, in dark energy, inertia, or even anomalous forces. Some researchers suggest that rotating vacuum energy could explain phenomena like inertia, mass generation, or even quantum entanglement if particles are indeed vortexes with connections extending across space. In conclusion, the idea that atoms are vortexes in the ether offers a fascinating alternative view of matter, not as static particles, but as condensed, stable rotations in a deeper quantum fabric. While this is not part of mainstream science today, it resonates with several modern theoretical developments that view reality as emergent, dynamic, and deeply interconnected. Whether it's fluid-like behavior in quantum fields or space-time foam at the Planck scale, this vortex model reminds us that matter might not be made of things, but of motion, structure, and twist. In the 19th century, scientists like Lord Kelvin and James Clerk Maxwell envisioned atoms as vortex structures in an all-pervading medium called the ether. These early models attempted to unify the mechanics of matter and field using fluid dynamics, where stable knots or vortices in the ether manifested as particles. Although ether theories were discarded after the advent of relativity and quantum mechanics, some modern approaches re-examine the idea of space as a structured, information-bearing substrate. In contemporary physics, vacuum fluctuations, zero-point energy, and quantum fields play roles once attributed to the ether. Vortex-like interpretations of matter are resurfacing within pilot wave theory, quantum turbulence, and emergent gravity frameworks. William Thomson, Lord Kelvin, proposed that chemical elements correspond to different vortex knots in an idealized fluid like ether, like tornadoes in air, seemingly solid and persistent, but actually rotating regions of an invisible medium. A vortex is a region where fluid circulates around an axis line, maintaining angular momentum and exhibiting topological stability. In both classical and quantum fluids, vortices can form discrete, quantized structures that persist and interact like particles. Superfluid helium and Bose-Einstein condensates, BECS, exhibit quantized vortex lines, suggesting that under certain conditions, fluid dynamics can mimic quantum phenomena. These systems display characteristics like phase coherence, long-range order, and rotational quantization that echo foundational principles of quantum particles. Thus, vortex models provide a bridge between continuum mechanics and discrete quantum structures. In a Beck trapped in a magnetic field, rotating the condensate creates quantized vortices that resemble miniature atomic structures. Like watching eddies form in a still pond when stirred, stable shapes arise from swirling motion in an otherwise uniform medium. In vortex-based models, atoms are not solid spheres or point particles, but standing waves or rotational structures in a fluidic or field-based medium. The apparent solidity of matter arises not from mass occupying space, but from energetic, topologically stable configurations of motion. Mass and charge could emerge as characteristics of how the vortex twists, knots, or interacts with surrounding space. This view aligns with quantum field theory interpretations where particles are excitations of an underlying field. Matter then is not substance, but behavior condensed into repeatable, self-sustaining patterns. The electron in quantum electrodynamics is treated as an excitation of the electron field, similar to how a vortex is an excitation in a fluid, like a whirlpool in water. There's nothing inside it, yet it has shape, motion, and persistence. In vortex models, intrinsic properties of particles such as mass and spin might originate from the nature of rotational motion within the medium. The angular momentum stored in a closed-loop vortex could be perceived externally as spin, and resistance to deformation could correspond to inertial mass. Charge may be an emergent effect of asymmetry or circulation direction, analogous to how magnetic fields arise from rotating charge. Like rotational origins provide a mechanical interpretation of what are otherwise abstract quantum numbers. This idea invites a deeper connection between dynamics and identity in the fabric of matter. In the Zitterbewegung interpretation of the Dirac equation, the electron exhibits a rapid oscillatory motion that could reflect internal rotation. Like the hum of a spinning top, the sound, balance, and resistance arise from invisible internal motion. Modern physics no longer uses the term ether, but the quantum vacuum plays a similar role as a background field with non-zero energy and structure. Quantum field theory suggests that what appears as empty space is actually a seething ocean of virtual particles and fluctuations. These fluctuations give rise to observable phenomena like the Casimir effect and spontaneous emission. In some interpretations, the quantum vacuum acts as a medium through which fields propagate and particles emerge, bearing resemblance to an informational ether. Vortex models, reinterpreted in this context, propose that atoms are rotating singularities within this quantum sea. The Lamb shift in hydrogen energy levels results from interactions between electrons and quantum vacuum fluctuations. Like waves on an unseen sea, objects float, dance, and rotate, carried by the invisible undercurrents of the void. Maxwell's equations allow for vortex-like structures in electromagnetic fields, and general relativity admits frame dragging and torsion, gravitational analogs of vortex motion. In some speculative models, particles like electrons are modeled as stable knots in combined electromagnetic and gravitational fields. These field-based vortices can trap energy and exhibit spin-like properties, linking classical field theory to quantum properties. Such configurations may explain stability and localization of matter without invoking solid constituents. They hint at a unified picture of forces and particles as structured energy flows. In the Einstein-Cartan theory, space-time torsion allows for rotating configurations of geometry that could model spinning particles. Like twistors in storm clouds, rotating patterns emerge from gradients and tension in the underlying field. Topological solitons are stable field configurations that cannot be continuously deformed into trivial states. In condensed matter and quantum computing, quasiparticles like skyrmions, anyons, and fluxons are modeled as knots or braids in field configurations. This topological stability mirrors the vortex atom idea, stability without mass achieved through geometric constraints in a medium. It also offers resilience against decoherence, making topological models attractive for quantum systems. These concepts revive the 19th century vortex hypothesis with a modern mathematical foundation. Anyons in 2D quantum Hall systems exhibit fractional statistics due to their topological braiding properties. Like tying knots in a rope, what holds them together is not glue or matter, but the impossibility of untying without cutting. No direct experimental evidence currently supports the idea that atoms are literal vortices in an ether-like medium. However, the success of analog models in superfluid helium, BECs, and photonic systems suggests that vortex-like behaviors can reproduce many particle properties. Emerging techniques in quantum simulation, field visualization, and space-time geometry might test aspects of these theories. A major challenge is defining what medium, if any, supports these vortices in a Lorentz invariant and quantum compellent way. Despite being speculative, the vortex model encourages fresh thinking about the fabric and dynamics of matter. Vortex reconnection and decay in quantum fluids have been used to model particle collisions and annihilation analogs, like watching shadows dance on the wall. Sometimes the patterns hint at a deeper geometry behind the surface. If atoms are vortices in an underlying field or medium, then matter itself may be a process, persistent rotating information rather than a substance. This paradigm replaces the notion of discrete particles with localized stability in a dynamic continuum. It aligns with process-based metaphysics and could unify seemingly unrelated concepts across quantum mechanics, fluid dynamics, and field theory. Even in standard physics, entities like solitons, wave packets, and field excitations suggest that what we call particles are better described by how they move and interact than what they are made of. In this view, mass, charge, and identity are not ingredients but expressions of organized rotation. The Higgs field imparts mass to particles not by giving them stuff, but by resisting their motion. Another example of mass as an emergent effect, like a whirl in a river. The shape stays, the water flows, and the identity is the movement itself.